50 million years ago, crocodiles swam at the North Pole. Not metaphorically, not in some distant ocean that would later drift northward through tectonic movement. Literally at the North Pole. At latitudes where today you find only ice, darkness and temperatures that will kill an unprotected human in minutes, there were crocodiles. 3.5-meter predators cruising through water that was 18 degrees Celsius, warmer than the North Sea is today. The sun hung low on the horizon, circling without ever setting, as it does during Arctic summer. But this wasn't a brief summer thaw. This was permanent, year-round warmth. The water surface was littered with debris, palm fronds, broad leaves from deciduous trees, seed pods from plants that shouldn't exist within 3,000 kilometers of the pole. But they did exist. You could see them lining the shores if you followed the crocodile's gaze. Metasequoia, dawn redwood, rising 35 meters, their feathery foliage bright green in the endless daylight. And between them, unmistakably, palms. Actual palm trees, their fan-shaped fronds silhouetted against a sky that carried a quality of light found nowhere else on Earth. This was the Eocene Arctic, and everything you think you know about polar ice, that it's ancient, permanent, an immutable feature of Earth's geography, is wrong. Before we dive in, please consider subscribing and liking this video. Your support truly helps us continue this work. Thank you. We're going to journey to a world where the rules were different, where the Arctic wasn't a frozen wasteland, but a jungle, where the absence of ice wasn't an anomaly, but the norm. We're going to examine the evidence: fossil forests preserved in permafrost, sediment cores drilled from the ocean floor, chemical signatures trapped in ancient shells. We're going to meet the scientists who discovered this impossible world and pieced together how it worked. And we're going to ask the question that matters most. Could it happen again? Because the physics that created the Eocene Arctic haven't changed. The mechanisms that warmed the poles to subtropical temperatures are still operational. And we are, right now, conducting an experiment to see what happens when you push atmospheric carbon dioxide back toward Eocene levels. Only much, much faster than it's ever been done before. This is the story of a world we've forgotten, and a warning about the world we're creating. The first hints that the Arctic had once been warm came in the mid-19th century, but nobody believed them. European explorers venturing into the Canadian Arctic and Greenland, men searching for the Northwest Passage or mapping uncharted territories, occasionally stumbled upon something inexplicable. Fossilized wood? Not small fragments or driftwood that might have floated from temperate regions, but large pieces, sometimes entire trunks, embedded in rock formations far above the Arctic Circle. Geologists who examined these specimens identified them as metasequoia and other trees associated with temperate climates. Trees that required warmth, regular precipitation, and growing seasons measured in months, not weeks. The immediate assumption was transport. Ocean currents or glaciers must have carried these trees north from their native habitats and deposited them in Arctic sediments. It was the only explanation that made sense. Everyone knew the Arctic was cold. It had always been cold. The ice caps were permanent features, remnants of the Ice Age perhaps, but fundamentally stable over geological time. The alternative, that forests had actually grown in situ at latitudes where the sun doesn't rise for months at a time, was absurd. But as the 20th century progressed and more fossils accumulated, the transport hypothesis became untenable. the fossils weren't scattered randomly as transported debris would be. They were concentrated in specific sedimentary layers corresponding to specific geological periods. They were found with root structures intact in ancient soil horizons. They were associated with fossilized pollen, seeds, leaves, entire plant assemblages that indicated local ecosystems, not isolated specimens washed in from elsewhere. Something extraordinary had happened in the Arctic, and scientists were only beginning to understand what. The breakthrough came in the 1980s on Ellesmere Island in the Canadian Arctic. Ellesmere is one of the most remote places on Earth. The northernmost island of the Canadian Arctic archipelago, it extends from roughly 76 degrees north to 83 degrees north latitude, well within the Arctic Circle, closer to the North Pole than to any major city. Today, it's a land of rock, ice, and tundra. Temperatures average minus 30 Celsius in winter, barely rising above freezing in the brief summer. Nothing taller than low shrubs grows there. Polar bears outnumber humans. It is, by any measure, one of the most inhospitable environments on the planet. In 1985, paleobotanist James Bassinger from the University of Saskatchewan led an expedition to Strathcona Fjord on Ellesmere's western coast. They were investigating Eocene age sediments, rocks formed between 56 and 34 million years ago, that earlier surveys had suggested might contain plant fossils. What they found exceeded anything they'd anticipated. Mummified stumps, dozens of them. Metasequoia trees, still standing in their original growth positions, roots extending into what had once been soil and was now permafrost. The wood was so well preserved by the Arctic's cold, dry conditions that you could see cellular structure under magnification. Growth rings were clearly visible, recording seasonal variations in ancient climatic conditions. And here's the astonishing part. The wood could still burn. 50-million-year-old trees, preserved well enough that if you held a match to them, they would ignite and give off heat and smoke, just like fresh-cut lumber. These weren't fossils in the traditional sense, minerals replacing organic material over millions of years. These were actual trees, freeze-dried by time and Arctic conditions into a state of suspended decay. The location was critical. Strathcona Fjord sits at approximately 82 degrees north latitude. For context, Alert, Canada, the northernmost permanently inhabited place on Earth, is at 82.5 degrees north. Bassinger's team had found thriving forests growing farther north than any human settlement, in a location that today experiences 5 months of continuous darkness each winter, and where the average annual temperature is minus 17 Celsius. But the growth rings told a different story. They showed rapid growth, several millimeters of wood added per year, comparable to modern temperate forests. The trees hadn't been struggling at the edge of habitability. They'd been thriving. And the species composition of the fossil assemblages, identified through leaves, seeds, and pollen preserved alongside the wood, included not just Metasequoia, but birch, alder, and relatives of modern ginkgo and dawn redwood. Dozens of species, forming complex forest ecosystems. The implications were staggering. These forests required mean annual temperatures of at least 10 to 12 degrees Celsius. Winter temperatures couldn't drop much below freezing, or the trees, especially the broadleaf deciduous species, wouldn't survive. And this warmth had persisted for millions of years, long enough for thick sedimentary deposits to accumulate, for ecosystems to establish and diversify, for evolution to shape species specifically adapted to polar conditions. The Arctic hadn't just been warm once, it had been warm for geological epochs. This wasn't an anomaly, it was a climate state. If the Ellesmere discoveries raised questions, the Arctic coring expedition of 2004 answered them, and raised even more profound ones. ACX was an ambitious international project led by the Integrated Ocean Drilling Program. The goal was to drill sediment cores from the floor of the Arctic Ocean itself, retrieving a continuous record of Arctic climate going back millions of years. The challenge was logistical. The Arctic Ocean is covered by permanent sea ice, or at least it was in 2004, before recent warming began opening seasonal passages. You can't drill from a stationary platform because the ice drifts, grinding against anything in its path with forces that crush steel. The solution was to use an icebreaker as a drilling platform. The Swedish icebreaker Vidar Viking, a massive vessel designed to force its way through multi-year ice, was equipped with drilling equipment capable of boring through hundreds of meters of seafloor sediment while maintaining position relative to the drill site. The expedition was co-led by Catherine Moran from the University of Rhode Island, Jan Backman from Stockholm University, and Henk Brinkhuis from Utrecht University. Scientists representing multiple disciplines and nations, coordinating a team of dozens of researchers. They targeted the Lomonosov Ridge, a submarine mountain range that stretches across the Arctic Ocean from Siberia to Greenland. It's a remnant of continental crust that split off from the Eurasian margin millions of years ago, and now sits at water depths of around 1,000 meters, shallow enough to drill, but deep enough that the sediments haven't been disturbed by ice scouring during recent glacial periods. In August 2004, the Vidar Viking reached its drilling site at approximately 87 degrees north latitude, just 300 kilometers from the North Pole. Over several weeks, operating in 24-hour daylight under difficult ice conditions, the team drilled a series of cores penetrating more than 400 meters into the seafloor, retrieving sediment spanning 56 million years of Arctic history. What they found in those cores rewrote our understanding of polar climate. The most dramatic discovery came from sediment layers dating to the Middle Eocene, around 49 million years ago. These layers were filled, absolutely saturated, with microscopic fossils of Azolla, a genus of small freshwater fern. Not just scattered specimens. Dense concentrations, billions upon billions of spores per cubic centimeter of sediment, forming distinct bands centimeters thick that could be traced across multiple drill sites. Azolla is a floating aquatic fern, barely a centimeter across, that lives on the surface of freshwater ponds and slow-moving rivers. It reproduces rapidly. Under ideal conditions, it can double its biomass every 2 to 3 days. It hosts symbiotic cyanobacteria in specialized cavities in its leaves, bacteria that fix nitrogen from the atmosphere, meaning the fern doesn't need nitrogen from the water to grow. Give it sunlight, calm water and warm temperatures, and Azolla will cover a water surface in a thick mat, blocking light from penetrating below. Finding Azolla in Arctic Ocean sediments was shocking. The Arctic Ocean is salt water. Azolla requires fresh water. So why was it there? The only explanation, 50 million years ago, the Arctic Ocean wasn't fully marine. Its surface layer was freshwater, or at least brackish enough for Azolla to survive. Rivers from surrounding continents, Siberia, North America, Greenland, were pouring fresh water into an enclosed basin. Because fresh water is less dense than salt water, it floated on top, creating a stable lens of low salinity water tens or hundreds of meters thick, sitting atop the denser, saltier, deep ocean. And Azolla had colonized it. Not just patches here and there, the entire Arctic Ocean. Millions of square kilometers of floating fern, forming a mat that may have been meters thick in places, persisting not for years or centuries, but for 800,000 years. The sediment layers record this event continuously through that entire period. The implications for climate were profound, but we'll return to that. What mattered immediately was what the Azolla discovery revealed about the Arctic Ocean itself. It had been warm enough to support lush vegetation. Deeper in the cores, in sediments dating to the late Paleocene and early Eocene, 56 to 50 million years ago, the team found biomarkers indicating sea surface temperatures of 18 to 23 degrees Celsius. That's warmer than the Mediterranean is today, at the North Pole. The Arctic Ocean hadn't just been ice-free, it had been a warm subtropical sea. Write in the comments what city you're watching from. I'm really curious to know. The fossil forests on land and the warm ocean revealed by sediment cores were extraordinary enough. But paleontologists working in Arctic regions over the past few decades have found something even more viscerally striking. The animals that lived there. Borealosuchus. The name means northern crocodile, and it's not metaphorical. This was a true crocodilian, a member of the same group that includes modern alligators and crocodiles, and its fossilized remains have been found in Eocene sediments on Ellesmere Island and in Greenland at latitudes exceeding 80 degrees north. Borealosuchus was a substantial predator, reaching lengths of 3.5 meters, comparable to a modern American alligator. Its skull morphology indicates it was semi-aquatic, spending time both in water and on land, and its teeth suggest a diet of fish, turtles, and possibly small mammals. Finding it in the Arctic is extraordinary because crocodilians are ectotherms, cold-blooded animals that depend on environmental warmth to regulate their body temperature. Modern crocodilians don't range farther north than about 35 degrees latitude because they can't tolerate prolonged cold. Their metabolic processes shut down if water temperatures drop below about 10 degrees Celsius, and they die if exposed to freezing conditions for extended periods. Yet Borealosuchus thrived at 82 degrees north. The only way that's possible is if Arctic waters never dropped below roughly 10 to 12 degrees Celsius, even during the months of polar night when the sun doesn't rise at all. The crocodiles are a living thermometer, their presence proof that the Arctic was warm year-round. They weren't alone. Fossil turtle shells belonging to the family Trionychidae, the soft-shell turtles, have been recovered from the same Eocene Arctic deposits. Trionychidae today are found in warm temperate to tropical regions of Asia, Africa, and North America. Like crocodilians, they require sustained warmth. Their presence reinforces the temperature estimates. The Arctic was warm. Then there are the mammals. Coryphodon, a bizarre extinct herbivore roughly the size and build of a hippopotamus with a body mass around 500 kilograms, has been found in Eocene Arctic sediments. Coryphodon was semi-aquatic, probably spending much of its time in or near water, feeding on aquatic vegetation. Its presence indicates not just warm temperatures, but abundant plant life, enough biomass to support large herbivores. Perhaps most astonishingly, paleontologists have found fossils of Teilhardina in Eocene Arctic deposits. Teilhardina was a primate. Yes, a primate. In the Arctic. Teilhardina was tiny, weighing perhaps 30 grams, about the size of a mouse lemur, and arboreal, living in trees. It's one of the earliest known primates, appearing in the fossil record right at the Paleocene-Eocene boundary around 56 million years ago. Fossils have been found across North America, Europe, and Asia, indicating a wide geographic distribution during a time of global warmth. But finding Teilhardina fossils at high Arctic latitudes, creatures that required forests, fruit or insect prey, and temperatures mild enough for year-round activity, underscores just how warm the Arctic was. These weren't stragglers or migrants that got lost and died. The density and diversity of fossils indicate thriving populations, stable ecosystems, predator-prey relationships. The Arctic supported communities of reptiles and mammals that today you'd find in places like Florida or Southeast Asia. So the question wasn't whether the Arctic was warm. The fossil evidence made that undeniable. The question was, how warm, precisely? And how do we know? Imagine oxygen atoms as dancers, one heavy, one light. Oxygen 16 is the light dancer, nimble and quick. Oxygen 18 is the heavy dancer, slower, more ponderous. Both exist in nature, but their ratio changes depending on temperature. When water evaporates, lighter oxygen 16 molecules escape more easily than heavier oxygen 18. So water vapor is enriched in light oxygen, and the water left behind is enriched in heavy oxygen. When that vapor condenses and falls as rain or snow, the heavy oxygen preferentially precipitates first. The result is that in colder climates, or during ice ages, the ice sheets that form are enriched in light oxygen 16, while the ocean becomes enriched in heavy oxygen 18. Marine organisms, foraminifera, mollusks, ostracods, build their shells from calcium carbonate dissolved in seawater. The oxygen in those shells reflects the isotopic composition of the water they lived in, which in turn reflects the temperature and ice volume at the time. By measuring the ratio of oxygen 18 to oxygen 16 in fossil shells, scientists can reconstruct ancient ocean temperatures. The technique was developed in the 1950s by Harold Urey and refined by Cesare Emiliani, Sam Epstein and others. By the 1980s and 90s, it had become the backbone of paleoclimate research. Scientists like James Zakos at UC Santa Cruz and Ellen Thomas at Yale applied it to deep-sea sediment cores spanning millions of years, building a continuous record of Earth's climate from the Cretaceous to the present. When applied to Eocene age sediments from the Arctic Ocean and surrounding seas, oxygen isotope ratios told a clear story. The shells of foraminifera, single-celled organisms that lived in surface waters, showed oxygen isotope signatures consistent with water temperatures of 18 to 23 degrees Celsius. For comparison, modern sea surface temperatures in the Caribbean average around 27 degrees Celsius, and in the Mediterranean around 20 to 24 degrees. The Eocene Arctic Ocean was as warm as the Mediterranean is today. Deep ocean temperatures were also remarkably warm, 10 to 12 degrees Celsius, compared to modern deep ocean temperatures of 2 to 4 degrees Celsius. The entire ocean, from surface to depth, was warmer. But oxygen isotopes have limitations. They're affected not just by temperature, but also by salinity and ice volume. During ice ages, for example, lighter oxygen gets locked in ice sheets, skewing the ocean's isotopic composition. Interpreting the data requires careful calibration and cross-checking with other methods. Enter organic geochemistry. In the 1990s and 2000s, researchers developed a new class of temperature proxies based on organic molecules preserved in sediments. One of the most powerful is TEX86, tetraether index of 86 carbon atoms. TEX86 is based on lipids produced by marine archaea, single-celled microorganisms that live throughout the ocean. These archaea build their cell membranes from molecules called glycerol dialkyl, glycerol tetraethers, or GDGTs. The structure of these molecules, specifically how many cyclopentane rings they contain, changes with temperature. In warmer water, archaea produce GDGTs with more rings, which makes their membranes less permeable and more stable. In cooler water, they produce GDGTs with fewer rings. When the archaea die, these lipids settle to the seafloor and are preserved in sediments for millions of years. By extracting and analyzing GDGTs from ancient sediment layers, scientists can reconstruct the temperature of the water in which the archaea lived. The beauty of TEX86 is that it's independent of oxygen isotopes. It doesn't care about salinity or ice volume. It's purely a function of temperature. And when applied to Arctic Ocean sediments by researchers like Appie Sluids at Utrecht University and Matthew Huber at Purdue University, TEX86 confirmed what the oxygen isotopes had suggested. Eocene Arctic sea surface temperatures were 18 to 23 degrees Celsius. But what about land temperatures? Ocean proxies tell us about the sea, but the forests on Ellesmere were growing on land. How warm was the air? Paleobotanists have a tool for that: leaf margin analysis. It's based on a simple observation that modern plant ecologists noticed decades ago. In warm climates, most trees have smooth-edged leaves. In cooler climates, a higher percentage have toothed leaf margins, serrations along the edges. The relationship is strong enough that you can estimate mean annual temperature from the percentage of species with smooth margins. When applied to fossil leaf assemblages from Eocene Arctic sites, leaf margin analysis indicates mean annual temperatures of 12 to 18 degrees Celsius. Winter lows were probably around 0 to 5 degrees Celsius. Cold, but not freezing for extended periods. Summer highs were around 20 to 25 degrees Celsius. For context, modern Arctic sites like Ellesmere Island have mean annual temperatures of -15 to -20 degrees Celsius, with winter lows reaching -40 and summer highs barely above 10 degrees. The Eocene Arctic wasn't just warmer, it was a different world. So what caused this warmth? The answer, overwhelmingly, is carbon dioxide. Carbon dioxide is a greenhouse gas. It's transparent to incoming visible light from the sun, but it absorbs outgoing infrared radiation, heat, emitted by Earth's surface. This trapped heat warms the atmosphere. The relationship between carbon dioxide and temperature has been understood since the work of Svante Arrhenius in the 1890s and has been refined through laboratory experiments, satellite observations, and climate models. The question is, how much carbon dioxide was in the Eocene atmosphere? We can't measure it directly. Ice cores, which trap tiny bubbles of ancient air, only go back 800,000 years, and the Eocene was 56 to 34 million years ago. But scientists have developed proxy methods. One uses boron isotopes in the shells of foraminifera. The ratio of boron-11 to boron-10 incorporated into calcium carbonate is sensitive to the pH of seawater, and ocean pH is controlled largely by atmospheric carbon dioxide. More carbon dioxide dissolves in the ocean, forming carbonic acid and lowering pH. By measuring boron isotopes in fossil shells, researchers can reconstruct ancient ocean pH and, from that, estimate atmospheric carbon dioxide. Another method uses carbon isotope ratios in marine sediments and paleosol carbonates, minerals formed in ancient soils. These ratios reflect the balance between different carbon sources and sinks, which is influenced by atmospheric carbon dioxide levels. A third method, developed more recently, uses the density of stomata, the microscopic pores on plant leaves through which they exchange gases. Plants regulate stomatal density based on carbon dioxide availability. When carbon dioxide is abundant, plants can get by with fewer stomata. When it's scarce, they need more. Fossil leaves preserve stomatal patterns, providing a direct botanical record of ancient atmospheric composition. All these methods, when applied to Eocene samples, converge on a consistent answer. Atmospheric carbon dioxide during the Eocene was between 1,000 and 2,000 parts per million. Some intervals might have been higher, others slightly lower, but the overall range is clear. For comparison, pre-industrial carbon dioxide, the level humanity lived with for thousands of years before burning fossil fuels, was 280 parts per million. Current levels, as of 2024, are around 420 parts per million. The Eocene was 3 to 5 times higher than pre-industrial levels. And the physics is straightforward. Double carbon dioxide from pre-industrial levels and global average temperature rises by about 3 degrees Celsius, a value known as climate sensitivity. Triple it, and you add another 3 degrees. Quadruple it, roughly 1,000 parts per million, and you're looking at 9 to 12 degrees Celsius of warming relative to pre-industrial. That's consistent with global Eocene temperatures, which were about 10 to 15 degrees warmer than today. But the warming wasn't uniform. Polar regions warmed more than the tropics, a phenomenon called polar amplification. Today, the Arctic is warming twice as fast as the global average, and during the Eocene, the same pattern held. The tropics might have been 28 to 32 degrees Celsius, similar to now, while the poles were 15 to 20 degrees. The equator to pole temperature gradient was much flatter than today. This had profound consequences. Here's the problem. At 82 degrees north latitude, the sun doesn't rise for 5 months every winter. From late October to late February, Ellesmere Island is in continuous darkness. Even at slightly lower latitudes, 75 to 80 degrees, you're looking at 3 to 4 months of no sunlight. Plants need light for photosynthesis. No light means no energy production, no growth, no survival. Modern trees, even cold-tolerant conifers, go dormant in winter, surviving on stored energy reserves built up during the growing season. But dormancy works in temperate and boreal climates, where winter lasts 3 or 4 months, not 5 or 6, and where at least some weak light persists even during the shortest days. How did Eocene Arctic forests, including palms, which are tropical plants intolerant of extended darkness, survive half a year without sunlight? The answer lies in adaptation, both physiological and ecological, and in the fact that even during polar night, conditions weren't entirely dark. First, deciduous trees, those that shed their leaves seasonally, could survive by going fully dormant. Metasequoia, the dominant tree in Eocene Arctic forests, is deciduous. It drops its needles every autumn and regrows them in spring. During winter dormancy, metabolic processes slow to a minimum. The tree survives on stored carbohydrates built up during the summer. Growth ring analysis of fossilized Metasequoia from Ellesmere shows clear patterns: wide, rapid growth bands corresponding to summer, and narrow or absent bands corresponding to winter. The trees essentially shut down for half the year. But what about evergreen plants, including palms and cycads, which don't shed leaves? These pose a greater challenge. Fossil evidence shows they were present in Eocene Arctic ecosystems, yet they required year-round energy. One hypothesis is that these plants relied on a combination of stored reserves and minimal winter photosynthesis. Even during polar night at latitudes below about 80 degrees, there are hours of twilight each day when the sun is just below the horizon. Scattered light illuminates the landscape, and while it's far too dim for efficient photosynthesis, it's not zero. Combined with moonlight, which during full moons can be surprisingly bright in snow-covered landscapes, and the faint glow from stars in the clear Arctic sky, some minimal light energy might have been available. More importantly, during the 6 months of continuous summer daylight, photosynthesis could operate nearly 24 hours a day. Growth would be compressed into a short, intense growing season, but the total annual energy capture might rival or even exceed that of temperate forests, where daylight is limited to 12 to 16 hours per day. Studies of modern Antarctic mosses and algae, which survive polar winters today, show that some photosynthetic organisms can enter a state of extreme metabolic suppression, reducing energy consumption to nearly zero for months at a time. Eocene Arctic plants may have evolved similar strategies. There's also the possibility that palms and other evergreens weren't surviving in place year-round, but rather regrowing from seeds or underground structures each spring. However, the presence of large mature palm trunks in the fossil record suggests at least some individuals persisted through multiple winters. Regardless of the specific mechanisms, and researchers are still debating details, the fact is that these plants did survive. The fossil evidence is unambiguous, and their survival tells us something critical. The Eocene Arctic climate was stable. Winters were dark, but not lethally cold. Summers provided enough light and warmth for rapid growth, and this stability persisted for millions of years. Imagine standing in an Eocene Arctic forest. It's midsummer, so the sun hangs low on the horizon, tracing a slow circle without setting. The air is warm, maybe 20 degrees Celsius, humid, thick with the scent of vegetation and decay. Around you, Metasequoia trees rise like pillars, their trunks a meter or more in diameter, their feathery green foliage forming a canopy 30 meters overhead. Sunlight filters through in dappled patterns, illuminating the understory. Between the Metasequoia are broad-leafed deciduous trees, relatives of modern birch, alder and ginkgo, their leaves rustling in a gentle breeze, and palms. Sabolites, a fossil genus related to modern palmetto palms, stands out incongruously, its fan-shaped fronds spreading above the lower canopy. Cycads grow nearby, their stout trunks topped with crowns of stiff, pinnate leaves. The forest floor is a tangle of ferns, some waist-high, others low and creeping. Mosses carpet the ground in moist areas. Flowering plants, early relatives of modern herbaceous species, dot the understory with splashes of color. Fallen logs, covered in fungi and lichens, decompose slowly, feeding nutrients back into the soil. The diversity is staggering. Paleobotanists analyzing fossil assemblages from Eocene Arctic sites have identified more than 30 tree species coexisting in these forests. For comparison, modern Arctic tundra has 0 tree species. Boreal forests farther south, in places like interior Alaska or Siberia, typically have 5 to 10 tree species. The Eocene Arctic forests rivaled temperate rainforests in diversity. And the biomass, the total mass of living plant matter per unit area, was comparable to modern temperate forests. Maybe even higher because of the extended daylight. During the summer growing season, with 24 hours of continuous sunlight, photosynthesis could operate around the clock. Trees grew fast, adding several millimeters of wood per year, rates that match or exceed modern temperate species. This productivity supported complex food webs. Herbivorous insects fed on leaves, seeds, and wood. Predatory insects hunted the herbivores. Amphibians and reptiles, frogs, salamanders, turtles, crocodiles, occupied aquatic and semi-aquatic niches. Mammals ranged from tiny primates like Tailhardina scampering in the canopy to massive Coryphodon wading through wetlands, feeding on aquatic vegetation. Birds filled the skies. Gastornis, a 2-meter-tall flightless bird with a massive beak, stalked the forest floor, possibly hunting or scavenging. Presbyonis, an early relative of ducks and geese, formed flocks along rivers and lakeshores. This wasn't a marginal ecosystem clinging to survival at the edge of habitability. This was a thriving, productive biome, as rich and complex as any tropical or temperate forest today. And it existed at latitudes where modern life is limited to lichens, mosses, and animals adapted to extreme cold. The productivity wasn't just impressive, it was higher than most modern ecosystems at similar latitudes. In fact, measurements from growth rings and biomass estimates suggest that Eocene Arctic forests may have been more productive than modern temperate forests, simply because photosynthesis could operate continuously during the growing season. 24 hours of daylight meant 24 hours of carbon fixation, energy capture, growth. The trees made the most of it. But here's the deeper question. Even with high carbon dioxide, even with greenhouse warming, how did the poles get warm enough to support crocodiles and palms? Why didn't heat remain concentrated at the equator as it does today? The answer lies in ocean circulation. Today, the Antarctic Circumpolar Current, the ACC, is the most powerful ocean current on Earth. It flows west to east around Antarctica, driven by westerly winds and unobstructed by any landmass. The ACC transports more water than any other current, about 135 million cubic meters per second, roughly 135 times the combined flow of all the world's rivers. But the ACC does more than move water. It acts as a barrier, thermally isolating Antarctica. Warm water from the tropics, carried poleward by other currents like the Gulf Stream or Kuroshio, can't penetrate the ACC. It's deflected and mixed before reaching the Antarctic continent. The result is that Antarctica remains cold, surrounded by cold water, which allows its ice sheets to persist. In the Eocene, the ACC didn't exist. Antarctica was still connected to South America via a land bridge or very shallow seaway. Australia, though separating, hadn't drifted far enough north to open a deep water passage. There was no circumpolar current. Instead, Warm water from the tropics could flow directly poleward, reaching the coasts of Antarctica and mixing with polar seas. The same was true in the north. The Arctic Ocean was more restricted than today, but it wasn't completely isolated. Warm water from the North Atlantic could flow in through passages between Greenland and Europe, delivering heat to high latitudes. The result was a much flatter equator-to-pole temperature gradient. Today, the difference between tropical and polar sea surface temperatures is about 25 to 30 degrees Celsius. In the Eocene, it was more like 10 to 15 degrees. Heat was distributed far more evenly across the globe. This flatter gradient had cascading effects on atmospheric circulation. Today, the steep temperature difference between equator and pole drives powerful jet streams, narrow bands of high-speed winds that flow west to east in the upper atmosphere. These jets steer storm systems and create the weather patterns we're familiar with. But jet streams are products of temperature gradients. Weaken the gradient, and the jets weaken too. In the Eocene, with less temperature difference between tropics and poles, atmospheric circulation was probably more sluggish. Jet streams were weaker, storms less intense, but heat transport was more consistent. Warm air from lower latitudes spread poleward more easily, and cold polar air didn't plunge as deeply toward the equator. The combination, warm ocean currents delivering heat to polar seas, and atmospheric circulation distributing warmth more evenly, created a climate where the poles could sustain forests and crocodiles. It was a self-reinforcing system. Warm poles meant no ice. No ice meant no ice albedo feedback, the process where white ice reflects sunlight back to space, cooling the surface. Without that feedback, warmth persisted. And with high carbon dioxide maintaining the greenhouse effect, the system remained stable for millions of years. But it wasn't constant. The Eocene lasted about 22 million years, from 56 to 34 million years ago. And during that span, climate varied. There were intervals even warmer than the baseline, and intervals that were slightly cooler. The most dramatic variation, the most extreme climate event of the entire Cenozoic era, occurred right at the beginning. 56 million years ago, something went catastrophically wrong. The Paleocene-Eocene thermal maximum. Geologists call it the PETM. It's one of the most intensively studied climate events in Earth's history, and for good reason. It's the closest geological analog we have to what's happening right now. The PETM began at the boundary between the Paleocene and Eocene epochs. Over a period of somewhere between 10,000 and 20,000 years, geologically instantaneous, global temperatures spiked by 5 to 8 degrees Celsius. That's on top of the already warm Paleocene baseline. The deep ocean, normally cold and stable, warmed by 4 to 5 degrees. Surface waters and land temperatures increased even more. The signature of the PETM is preserved in sediments around the world. It appears as a sharp negative excursion in carbon isotope ratios, a sudden drop in the ratio of carbon-13 to carbon-12 in marine carbonates and organic matter. This carbon isotope excursion, or CIE, is the defining marker of the event. It tells us that a massive amount of carbon, depleted in carbon-13, was injected into the atmosphere and oceans in a very short time. The carbon source was isotopically light, meaning it came from organic material, fossil carbon essentially, not from volcanic CO2, which has a different isotopic signature. The leading hypothesis for the carbon source is methane hydrates. Methane hydrates are ice-like structures formed from methane and water, stable only under conditions of low temperature and high pressure. They exist in enormous quantities on the ocean floor, particularly along continental margins and in permafrost soils. When hydrates destabilize, if temperatures rise enough or pressure drops, they release methane, a potent greenhouse gas. Methane in the atmosphere oxidizes to carbon dioxide over a decade or so, but during that time, it's extremely effective at trapping heat. One molecule of methane has roughly 80 times the warming potential of one molecule of CO2 over a 20-year timescale. So what triggered the hydrate release? The most likely candidate is volcanism. Specifically, the North Atlantic Igneous Province, a massive burst of volcanic activity associated with the opening of the North Atlantic Ocean as Greenland separated from Europe. This wasn't ordinary volcanism. It was flood basalts, huge volumes of lava erupting over geologically short periods, releasing thousands of gigatons of carbon dioxide into the atmosphere. The volcanic CO2 would have caused initial warming. That warming heated the oceans. Warmer oceans destabilized methane hydrates on the seafloor. The methane released caused more warming. More warming released more methane. A runaway feedback limited only by the total amount of hydrates accessible to destabilization. The evidence is compelling. Volcanic ash layers from the North Atlantic Igneous Province appear in sediments just below the PETM boundary. The timing matches, and the total amount of carbon released during the PETM, estimated from the magnitude and duration of the CIE, is somewhere between 3,000 and 7,000 gigatons. For context, humans have released about 650 gigatons of carbon since the Industrial Revolution. The PETM released 5 to 10 times that amount. But here's the critical difference. The PETM release took 10 to 20,000 years. Our release has taken 200 years. We're injecting carbon into the atmosphere 15 to 30 times faster than the PETM. The effects of the PETM were global and profound. Ocean acidification occurred as massive amounts of CO2 dissolved in seawater, forming carbonic acid. The pH of the ocean dropped significantly, enough to dissolve calcium carbonate on the seafloor. Deep-sea sediments from the PETM show a dissolution layer where carbonate shells were eaten away by acidic water. Benthic foraminifera, single-celled organisms living on the seafloor, experienced extinction rates of 30 to 50%. It was a mass die-off in the deep ocean. On land, the effects were equally dramatic but different. Low latitudes became almost unbearably hot. Paleoclimate models and proxy data suggest that tropical and subtropical regions experience temperatures exceeding 40 degrees Celsius during summer, close to the physiological limits for many mammals. Some regions may have become uninhabitable, at least seasonally. Fossil evidence shows significant mammal turnover during the PETM. Many species went extinct or migrated to higher latitudes where temperatures were more tolerable. And here's something fascinating. Mammals got smaller. This phenomenon, called the PETM dwarfing effect, is well documented. Early horses, Siphohippus, a dog-sized ancestor of modern horses, shrank by about 30% in body size during the PETM, then returned to normal size after temperatures declined. The same pattern appears in primates and other mammal groups. Why? Smaller bodies have higher surface area to volume ratios, which makes it easier to dissipate heat. In extremely hot climates, being small is an advantage. Evolution responded to heat stress by selecting for smaller individuals. But while low latitudes suffered, high latitudes thrived. The Arctic and Antarctic became even warmer, even more hospitable. Forests expanded. Biodiversity increased. Many of the tropical and subtropical species we find in Eocene Arctic deposits probably colonized during or immediately after the PETM, when warmth peaked and migration routes opened. The crocodiles, the palms, the primates, they may have reached the poles during this interval. The PETM turned the Arctic into a paradise for organisms adapted to warmth. The recovery from the PETM took 100,000 to 200,000 years. Carbon was slowly removed from the atmosphere through natural processes. Weathering of rocks consumed CO2. Forests expanded, absorbing carbon through photosynthesis. Dead organic matter was buried in sediments, locking carbon away. The ocean's buffering capacity, its ability to absorb and neutralize CO2, gradually restored pH balance. Temperatures declined back toward pre-PTM levels. Ecosystems recovered, though they were transformed. New species had evolved, old ones had gone extinct, and the distribution of life had shifted. But the Arctic remained warm. The PETM was an extreme event superimposed on an already warm baseline. After it ended, the Eocene greenhouse continued. For another 20 million years, the poles stayed forested, the oceans stayed warm, and carbon dioxide remained high, until something extraordinary happened, something that would begin the long process of returning Earth to an icehouse state. And it started, improbably, with a fern. Around 49 million years ago, during the Middle Eocene, the Arctic Ocean transformed into one of the strangest ecosystems Earth has ever seen. Picture this. The planet is overheating. Temperatures are elevated worldwide. The oceans are warm, even at the poles. Carbon dioxide levels are high, still around 1,000 to 1,200 parts per million. And then, from seemingly nowhere, a microscopic fern begins what may be the greatest carbon capture experiment in Earth's history. In 800,000 years, it will pull enough CO2 from the atmosphere to cool the entire planet. This is nature's last-ditch effort to reverse runaway warmth. And against all odds, it worked. The fern was Azolla, the same genus whose spores filled the sediment cores drilled by the ACX expedition. But this wasn't a modest bloom. This was an event so massive, so prolonged, that it left an indelible mark in the geological record. To understand why it happened, we need to understand the conditions in the Arctic Ocean at the time. The Arctic was an enclosed basin surrounded by the land masses of North America, Greenland, and Eurasia. Unlike today, where the Arctic Ocean connects broadly to the Atlantic and Pacific, the Eocene Arctic had restricted connections to the world ocean. Water could flow in and out, but not freely. Rivers from surrounding continents, massive rivers draining the interiors of Siberia, North America, and Greenland, poured fresh water into this enclosed basin. Normally, fresh water mixes with seawater, and the basin remains marine. But if the influx of fresh water is large enough, and the connection to the ocean restricted enough, something unusual happens. The fresh water doesn't mix, it floats. Because fresh water is less dense than salt water, it forms a stable layer on top of the denser, saltier water below. This is called stratification, and it creates, in effect, a giant freshwater lake sitting atop an ocean. That's what happened in the Middle Eocene Arctic. The surface layer, tens or even hundreds of meters thick, became brackish or nearly fresh. And Azolla, which requires fresh water to survive, found ideal conditions. Azolla is a remarkable plant. It's tiny. Each individual frond is maybe a centimeter across, but it reproduces explosively. Under ideal conditions, with warm water, abundant sunlight, and nutrients, Azolla can double its biomass every 2 to 3 days. It spreads across a water surface like a living carpet, blocking light from penetrating below. And critically, Azolla hosts symbiotic cyanobacteria in tiny pockets within its leaves. These bacteria fix nitrogen from the atmosphere, converting it into a form the plant can use. That means Azolla doesn't need nitrogen from the water. It's self-sufficient, capable of thriving even in nutrient-poor environments. Once Azolla colonized the Arctic Ocean's freshwater surface, it exploded. Within years, probably within decades, it covered the entire basin, millions of square kilometers, a floating mat of vegetation, possibly meters thick in places. And it persisted, not for a few years or centuries, but for 800,000 years. The sediment cores show continuous deposition of Azolla spores throughout this entire interval. Billions upon billions of spores per cubic centimeter, layer after layer, recording the presence of this fern blanket year after year, millennium after millennium. What did this do to the Arctic Ocean ecosystem? It devastated it. The fern mat blocked sunlight from penetrating the water below. Photosynthetic organisms in the water column, phytoplankton, algae, died off. Without photosynthesis, there was no oxygen production. The water below the fern mat became anoxic, devoid of oxygen. Fish, invertebrates, anything that needed oxygen to survive either migrated away or died. The Arctic Ocean became a dead zone beneath a living carpet. But that anoxia had an unintended consequence that would alter the planet's climate. When Azolla died, and individual fronds were constantly dying as new ones grew, the dead material sank. In oxygenated water, bacteria would decompose it, breaking down the organic matter and releasing the carbon back into the atmosphere as CO2. But in anoxic water, decomposition doesn't happen. There are no oxygen-breathing bacteria to do the work. The dead Azolla sank to the seafloor and was buried in sediment without decomposing. The carbon it had absorbed from the atmosphere through photosynthesis, carbon pulled out of CO2 during the fern's growth, was locked away, removed from the carbon cycle, sequestered in what would eventually become rock. Over 800,000 years, this process buried an estimated several hundred gigatons of carbon. To put that in perspective, the entire terrestrial biosphere, all the plants, trees, and soil organic matter on land today, contains about 550 gigatons of carbon. The Azolla event sequestered roughly that much, all in one ocean basin, over less than 1 million years. The effect on atmospheric CO2 was dramatic. Estimates suggest the Azolla event reduced atmospheric carbon dioxide by 200 to 400 parts per million. That's a massive drawdown. It's equivalent to removing all the CO2 humans have added to the atmosphere since industrialization, and then some. And temperatures responded. As CO2 declined, so did global temperatures. Not instantly. Climate systems have inertia, and it takes time for the planet to equilibrate to new CO2 levels. But over tens of thousands of years, the greenhouse effect weakened. The Middle Eocene thermal peak, when temperatures had been at their highest, gave way to a gradual cooling trend. This was the beginning of the transition from the Eocene greenhouse to the cooler climates of the later Cenozoic. The Azolla event didn't end the greenhouse world, but it initiated the decline. It was nature's desperate, unintentional geoengineering project, executed by an organism that weighs less than a gram. Eventually, the Azolla event ended. Why? Probably because the conditions that sustained it changed. Ocean circulation patterns shifted. The freshwater lens destabilized, perhaps due to increased mixing with deeper, saltier water. Salinity increased, and Azolla, which requires fresh water, could no longer survive. The bloom collapsed, but the carbon it had buried remained locked in sediments. The cooling it triggered continued, and Earth entered the late Eocene, a period of continued warmth, but with the first hints of the ice ages to come. The Arctic remained forested. Crocodiles still swam in polar seas. But the climate was no longer as extreme as it had been. The peak of Eocene warmth was past. For another 15 million years, the Eocene continued. The Arctic stayed warm, though not as warm as during the PETM or the Middle Eocene peak. Forests persisted. Metasequoia still grew at 80 degrees north. Crocodiles still hunted in polar waters. But the trend was clear. Temperatures were declining. Carbon dioxide was dropping. By the late Eocene, around 38 to 34 million years ago, CO2 had fallen to somewhere between 500 and 700 parts per million, still far above pre-industrial levels, still enough to maintain a greenhouse climate, but lower than it had been for tens of millions of years. And then, 34 million years ago, the climate crossed a threshold. Antarctica began to freeze. The transition happened fast, geologically speaking. Within 100,000 to 400,000 years, Antarctica went from a forested continent with temperate climates to an ice-covered landmass. The ice sheet that formed wasn't small. It was massive, kilometers thick in places, covering most of the continent. And once it formed, it didn't melt. It's still there today, 3.5 million years later, a remnant of that ancient freeze. What triggered it? The answer lies in tectonics and ocean circulation. Antarctica hadn't always been an isolated continent. For most of the Mesozoic and early Cenozoic, it was connected to other landmasses. During the Cretaceous and Paleocene, it was joined to South America via a land bridge. Australia was also attached or very close, separated only by narrow seaways. These connections meant that ocean currents from lower latitudes could reach Antarctica, delivering warm water to its coasts. But plate tectonics never stops. Continents drift. And by the late Eocene, the connections were breaking. The critical event was the opening of the Drake Passage, the gap between the southern tip of South America and the Antarctic Peninsula. This passage is about 800 kilometers wide today, but it didn't exist for most of Earth's history. South America and Antarctica were joined or separated by only a shallow, narrow seaway that restricted deep ocean flow. Around 35 to 30 million years ago, tectonic forces widened the Drake Passage enough for deep water to flow through. At roughly the same time, the gap between Australia and Antarctica also widened as Australia drifted northward. These openings allowed something unprecedented, the formation of the Antarctic Circumpolar Current. For the first time in Earth's history, an ocean current could flow unobstructed all the way around a continent. The ACC, driven by powerful westerly winds in the Southern Ocean, began to flow west to east around Antarctica, and it acted as a barrier. Warm water from the tropics, which had previously flowed south along the coasts of South America and Australia to reach Antarctica, was now blocked. It was deflected by the circumpolar current, mixed and cooled before it could reach the continent. Antarctica became thermally isolated, surrounded by a ring of cold water. With warm water delivery cut off and with carbon dioxide continuing to decline, Antarctic temperatures dropped. Snow that fell in winter no longer melted completely in summer. It accumulated. Over thousands of years, it compacted into ice. And once ice began to form, a feedback took over. The ice albedo feedback. Ice is white. It reflects sunlight. About 80 to 90% of incoming solar radiation bounces back to space rather than being absorbed. The more ice that formed, the more sunlight was reflected. The more sunlight reflected, the cooler the surface became. The cooler it became, the more ice formed. It was a runaway process, limited only by the size of the continent. The evidence for this rapid glaciation is preserved in deep-sea sediment cores from around the world. Scientists measure oxygen isotope ratios in the shells of foraminifera, those same single-celled organisms we discussed earlier. During glaciation, light oxygen-16 gets preferentially locked into ice sheets, leaving the ocean enriched in heavy oxygen-18. The isotopic composition of forum shells shifts accordingly. At the Eocene-Oligocene boundary, 34 million years ago, there's a sharp, sudden shift in oxygen isotope ratios in deep-sea cores globally. It's called the OI1 event, Oligocene Isotope Event 1. It represents the formation of the Antarctic ice sheet. Within a few 100,000 years, a geological eye blink, the planet went from ice-free poles to a world with a massive ice cap covering an entire continent. The effects rippled globally. Sea level dropped by 50 to 70 meters as water was locked up in ice. Coastlines retreated. Shallow seas that had covered parts of continents drained. Ocean circulation changed as cold, dense water began sinking around Antarctica, driving new deep ocean currents. And the equator to pole temperature gradient steepened dramatically. Now there was a cold pole, the flat gradient of the Eocene, where tropics and poles were separated by only 10 to 15 degrees, gave way to a steep gradient approaching modern values. That strengthened atmospheric circulation. Jet streams intensified, storm tracks shifted, the climate system entered a new mode. On land, the effects were equally profound, especially in the northern hemisphere. Europe experienced a dramatic extinction event called the Grande Coupure, the Great Cut. It occurred at about 33.9 million years ago, right at the Eocene-Oligocene boundary. Subtropical and warm-temperate mammal species that had dominated European ecosystems for millions of years suddenly vanished. They were replaced by migrants from Asia, species adapted to cooler, more seasonal climates. The Grande Coupure wasn't a meteor impact or volcanic catastrophe. It was climate change. The cooling triggered by Antarctic glaciation propagated northward, transforming ecosystems across the globe. But here's the remarkable thing. The Arctic didn't freeze. Not yet. Antarctica went from forested to ice-covered in a few 100,000 years. But the Arctic remained warm for another 30 million years. Why? The answer is geography. Antarctica is a continent surrounded by ocean. Once the circumpolar current formed, it could be completely isolated. No warm water reached it. The Arctic, by contrast, is an ocean surrounded by continents. It's connected to the Atlantic and Pacific. Ocean currents from lower latitudes, precursors to the modern Gulf Stream and other systems, could still deliver some heat to the north. The Arctic cooled, certainly. Forests became less diverse. The palms disappeared. Crocodiles went extinct at high latitudes. But trees still grew beyond the Arctic Circle. the Arctic Ocean remained ice-free. It wasn't until about 3 million years ago, during the Pliocene, that the Arctic finally froze. The trigger was another tectonic event, the closure of the Isthmus of Panama. For most of the Cenozoic, North and South America were separated by a seaway connecting the Pacific and Atlantic Oceans. Warm water from the Pacific could flow into the Atlantic, delivering heat to the North Atlantic and Arctic. Around 3 million years ago, the isthmus closed, blocking this flow. Ocean circulation reorganized. The Gulf Stream intensified, but its heat was concentrated in the North Atlantic rather than reaching the Arctic. Combined with continued low CO2 levels, by the Pliocene, atmospheric carbon dioxide had dropped to around 280 to 400 parts per million, similar to pre-industrial values. The Arctic finally crossed its own threshold. Sea ice began to form. Glaciers spread across Greenland and Arctic islands. And within a few 100,000 years, the Arctic ice cap existed. The transition from the Eocene greenhouse to the modern icehouse took 30 million years. It began with the Azolla event, which drew down CO2. It continued through the late Eocene as carbon dioxide declined further due to weathering, organic burial, and possibly changes in volcanic outgassing. It accelerated dramatically at 34 million years ago when Antarctica froze. And it concluded 3 million years ago when the Arctic froze. For the last 3 million years, Earth has been in an icehouse state, with ice caps at both poles and a climate characterized by ice age cycles, periodic advances and retreats of continental ice sheets, driven by orbital variations. This is the climate we know, the climate in which human civilization developed. For the 10,000 years of the Holocene, the current interglacial period, temperatures have been stable, sea level has been stable, and ice caps have been present but not advancing. Every city we've built, every agricultural system we've developed, every assumption we make about where to live and how to grow food is calibrated to this climate. But the Eocene teaches us something critical. This is not the only climate Earth can have. It's not even the normal climate. For most of the last 100 million years, Earth was warmer, much warmer. Ice caps are the exception, not the rule. So, here's the question. Could the Eocene climate return? We're currently at 420 parts per million CO2, heading toward 500 or 600 by the end of this century if emissions continue on their current trajectory. The Eocene ranged from 1,000 to 2,000 parts per million. We're not there yet, but we're moving in that direction. And we're doing it faster than any natural process in the geological record, except possibly certain massive volcanic events. The PETM, the fastest natural warming event in the Cenozoic, released carbon at a rate of about 0.3 to 0.6 gigatons per year. Humans are currently releasing about 10 gigatons per year. We're injecting carbon into the atmosphere 15 to 30 times faster than the PETM. What happens if we reach Eocene CO2 levels? The ice melts. All of it. Greenland contains enough ice to raise sea level by 7 meters. Antarctica contains enough for 58 meters. Melting it all would take centuries to millennia. Ice sheets respond slowly to warming, but the process would be inexorable. And long before complete melting, we'd experience meters of sea level rise from partial melting. Coastal cities, New York, Miami, Shanghai, Mumbai, Amsterdam, would be inundated. Hundreds of millions of people would be displaced. Agricultural zones would shift poleward. Some regions would become too hot for human habitation. But there are more immediate effects. As Arctic ice melts, and it's already melting faster than climate models predicted, freshwater floods into the North Atlantic. This freshwater is less dense than seawater, so it floats on top, just like the Eocene Arctic freshwater lens. And it disrupts the Atlantic meridional overturning circulation, or epoch, the current system that includes the Gulf Stream. The epoch depends on cold, salty water sinking in the North Atlantic. That sinking drives the circulation. Freshwater influx dilutes the salinity, weakens the sinking, and slows the entire system. If the epoch weakens significantly, Europe could cool even as the globe warms, because the Gulf Stream delivers heat northward. Weaken it, and Europe loses that heat source. There are other feedbacks. Warming Arctic permafrost is already releasing methane and carbon dioxide. Permafrost contains an estimated 1,600 gigatons of carbon, more than twice what's currently in the atmosphere. As it thaws, that carbon escapes, adding to atmospheric greenhouse gases, causing more warming, thawing more permafrost. It's the same runaway feedback that triggered the PETM, just slower. Arctic sea ice loss reduces albedo, accelerating warming. Changes in atmospheric circulation due to a weaker equator to pole gradient could alter storm tracks, rainfall patterns, monsoons. The physics doesn't care. Add enough CO2 and the planet warms. Warm it enough and ice melts. Melt the ice and albedo decreases, amplifying warming. Release enough carbon from permafrost and hydrates, and feedbacks take over. The system finds a new equilibrium. That equilibrium, if we push far enough, looks like the Eocene. A warm world, ice-free poles, forests in the Arctic. Crocodiles won't return to the North Pole. Evolution has moved on, and modern species are different. But the physical conditions could be similar. The question isn't whether Earth can be that warm. We know it can. The Eocene proves it. The question is whether human civilization can survive the transition. The Eocene was a stable, warm state that persisted for millions of years. We're creating a rapid transition from cold to warm over mere centuries. Ecosystems can't adapt that fast. Species can't migrate that quickly. Forests can't move poleward at the pace we're warming the planet. During the Eocene, change happened over thousands to millions of years. Evolution had time to work. Migration routes opened gradually. Now we're compressing that change into decades. Human infrastructure is even less mobile. We've built trillions of dollars of assets on coastlines, assuming sea level won't rise. We've established agricultural zones, assuming rainfall and temperature will stay within certain bounds. We've constructed water systems, power grids, transportation networks, all calibrated to current climate. Rapid change breaks these systems. And unlike natural ecosystems, human systems can't evolve. They have to be rebuilt at enormous cost. The Eocene Arctic lasted 22 million years. The crocodiles and palms thrived for millions of years in a stable, warm climate. Then conditions changed. CO2 declined. Ocean circulation shifted. Ice formed. The greenhouse ended. Now we're changing conditions again, pushing CO2 back toward Eocene levels, just orders of magnitude faster. The planet will respond. It has no choice. The physics is inexorable. Raise CO2, temperature rises. Melt ice, albedo decreases. Temperature rises faster. Release carbon from permafrost, CO2 and methane increase. Temperature rises faster still. But we can control the rate and the magnitude. We can choose how much carbon to emit, how fast. We can choose whether to stop at 500 parts per million or push to 1,000 or beyond. And that choice determines whether the transition is manageable, difficult, disruptive, costly, but survivable, or catastrophic. The Eocene tells us that Earth can be warm. It's been there before. It will adjust to whatever atmospheric composition we create, finding a new equilibrium. Life will persist. Not the same species, perhaps, but life nonetheless. Evolution will continue. But human civilization depends on stability. Our 10,000 years of agriculture, cities, and technology occurred during an unusually stable interglacial period. We're adapted to this climate. Move it too far, too fast, and we face challenges our ancestors never imagined. Standing among the fossil stumps on Ellesmere Island, you can hold a piece of mummified metasequoia wood in your hand. It's 50 million years old, but it feels like wood. You can see the grain, the growth rings, the cellular structure preserved by Arctic cold. It's organic. It was once alive. And you realize, this tree grew when the Arctic was a different world, when the rules were different, when life thrived where now there is only ice and barren rock. The tree didn't know it was living in an unusual time. The crocodiles swimming through warm Arctic waters didn't know that millions of years later, its bones would be frozen in permafrost, excavated by creatures who would marvel at the impossibility of its existence there. We have the knowledge they lacked. We know what we're doing. We know the trajectory. We know the consequences. We can see what's coming. The question is whether we'll use that knowledge. The Eocene Arctic is a glimpse of a warmer world. Not a future, exactly, but a possibility. A demonstration of what Earth looks like under different rules. And a reminder that the rules can change, have changed, are changing now. The Eocene Arctic is gone, but its lessons remain. In the fossils, in the geochemistry, in the sediment cores, in the knowledge that Earth can be radically different from what we've known, and in the warning that we are, right now, conducting an experiment to see what happens when you change the rules. The crocodile swimming through warm Arctic waters didn't have a choice. It lived in the world it was given. We have a choice. We can see what's coming. We can understand the physics. We can control, if we act, how fast and how far we push the system. The Arctic was once a jungle. It could be again. But what we do in the next few decades will determine whether that transformation takes millennia, time enough to adapt, to migrate, to adjust, or centuries, fast enough to overwhelm our capacity to respond. The Eocene teaches us that change is inevitable. Climate is never static. Earth moves between states. But it also teaches us that the rate of change matters. Slow change allows adaptation. Rapid change causes extinction. Choose the rate. Choose wisely. Because the planet doesn't care which equilibrium it settles into. But we should. Thank you for watching. If this changed your perspective on climate, on deep time, on the impermanence of the conditions we take for granted, please subscribe. Share this with someone who needs to understand that the planet we inhabit is not fixed, that change is constant, and that our choices matter. The Eocene Arctic is gone, but the mechanisms that created it are still here. The physics hasn't changed, only the timeline has, and that timeline is up to us. The future isn't predetermined. We're writing it now. Choose wisely.